main purpose of configuration management is to quickly spin up new resources whenever required. You may need to quickly spin up resources to upgrade to new instance types, to replace a failed instance or underperforming instance, for disaster recovery, for auto-scaling. You may also need to deploy configuration changes to a fleet of existing and running instances. Logging into each virtual machine and updating the same configuration files can take a ridiculous amount of time. So the deployment of the instances must be automated and repeatable to make the process easy and convenient. AWS supports a number of technologies for configuring and deploying Amazon EC2 instances and other AWS infrastructure. User data, Amazon Machine Images or AMIs, configuration management tools. User data is basically a command sequence that is executed at the first launch of the instance. When you launch an instance in Amazon EC2, you have the option of passing user data to the instance that can be used to perform common automated configuration tasks and even run scripts after the instance starts. You can pass two types of user data to Amazon EC2: shell scripts and cloud init directives. You can also pass this data into the launch wizard as plain text file for launching instances via the command line tools, or as base64 encoded text for API calls. The AMI provides the information required to launch an instance, which is a virtual server in the cloud. You can specify an AMI when you launch an instance, and you can launch as many instances from the AMI as you need. You can customize the instance that you launch from a public AMI and then save that configuration as a custom AMI for your own use. Instances that you launch from your AMI can use all the customizations that you've made. AWS also offers a variety of its own configuration management tools and services, which allow you to configure new instances using reusable templates and update configuration dynamically in response to change. In this lesson, we'll review some of these tools, such as AWS CloudFormation and AWS OpsWorks, and discuss strategies for combining these technologies into a comprehensive configuration and deployment strategy. AWS CloudFormation enables customers to create and modify collections of AWS resources using predefined reusable infrastructure templates. The CloudFormation templates provide EC2 bootstrapping features to help automate the initial installation and configuration of the OS and application stack. Templates can also be versioned, enabling customers to apply versioning logic to their AWS infrastructure the same way they do with software. AWS OpsWorks is a fully managed application stack management service that includes provisioning and configuration of Amazon EC2 instances, auto-scaling, application deployment, and application health monitoring. It also provides the ability to integrate with additional AWS services, such as Elastic Load Balancing and Amazon RDS instances. Your organization may have decided that it wants a base set of software included on all instances launched within its cloud. This may include homegrown utilities, in-house tools for using AWS services, and advanced software for enterprise-scale activities, such as monitoring and intrusion detection, among other possibilities. In this circumstance, consider using the base AMI approach. With this approach, you can pre-configure all of the software your organization requires on an Amazon EC2 instance, and then create an AMI from that instance. The new AMI would then become the AMI used to create all new instances within the organization. Organizationally, you could enforce use of the base AMI in a couple of ways. Create a custom toolset that becomes the gateway toolset for creating AWS resources, and that forces creation of instances from the pool of custom AMIs. Create processes that scan the running Amazon EC2 instances in your account and terminate any instances that are not using the standard AMIs. Third-party configuration tools, such as Chef and Puppet, are used by many AWS customers to start new Amazon EC2 instances in an automated and repeatable manner. The flexibility of these environments enables the implementation of a complete configuration management system. This screen illustrates one way in which configuration software can be integrated within an AWS architecture. Let's assume that you want to use configuration software to initialize a set of Amazon EC2 instances as web servers. The scenario breaks down as follows. The administrator sets up a configuration server. This usually is a standalone Amazon EC2 instance that will contain a set of templates which describe all of the applications, files, and configuration that a server needs to initialize itself. For example, a web server might instruct an instance to install Apache HTTPD, configure Apache's HTTPD config file, install all necessary programming language environments such as PHP, Ruby, and create a directory and file structure for web server content. A configuration server will likely contain a number of recipes for configuring dozens of different types of machines, including MySQL Server, NAT Server, Windows IIS Server, and so on. The administrator will create configuration templates, publish them to the configuration server, and check them into a source control system for version management and change tracking. The administrator will use custom scripting, CloudFormation, OpsWorks, or similar products to describe and create a full AWS cloud deployment environment. These tools may also specify what custom applications will be hosted in these environments, on which instances they should be hosted, and how they ought to be configured on each instance. For each Amazon EC2 instance that is deployed, the administrator will instruct the instance on how to configure itself as a configuration client of the configuration server. The administrator will also supply the name of the templates to be downloaded and executed on that machine. When an Amazon EC2 instance is deployed using a deployment technology, such as a script or CloudFormation, it will configure itself as a configuration client, download the appropriate template, and execute it. Various customers use different combinations of the technologies discussed in this topic to manage their AMIs. The solution adopted by your organization will depend on several factors, including your production workflow and your organizational standards. None of these techniques are mutually exclusive. They can all be used in tandem to craft a strategy that's right for your company. In general, placing software in AMIs is best reserved for foundational, slow-changing components that are truly required as standards throughout your organization. To create an Amazon EBS-Backed Linux AMI, start from an instance you've launched from an existing Amazon EBS-Backed Linux AMI. After you've customized the instance to suit your needs, create and register a new AMI, which you can use to launch new instances with these customizations. Ensure data integrity by stopping the instance before you create an AMI, then create the image. When you create an Amazon EBS-Backed AMI, it's automatically registered for you. Amazon EC2 powers down the instance before creating the AMI to ensure that everything on the instance is stopped and in a consistent state during the creation process. Some file systems, such as XFS, can freeze and unfreeze activity, making it safe to create the image without rebooting the instance. When you need to automate the creation of an AMI, you can use the AWS EC2 Create Image command as displayed on the screen. During the AMI creation process, Amazon EC2 creates snapshots of your instance's root volume and any other EBS volumes attached to your instance. If any volumes attached to the instance are encrypted, the new AMI will only launch successfully on instances that support Amazon EBS encryption. Depending on the size of the volumes, it can take several minutes for the AMI creation process to complete, sometimes up to 24 hours. You may find it more efficient to create snapshots of your volumes prior to creating your AMI. This way, only small, incremental snapshots need to be created when the AMI is created, and the process completes quickly, though the total time for snapshot creation remains the same. After the process completes, you have a new AMI and snapshot created from the root volume of the instance. When you launch an instance using the new AMI, a new EBS volume for its root volume is created using the snapshot. Both the AMI and the snapshot will accrue charges to your account until you delete them. You can copy an AMI within or across an AWS region using the AWS Management Console, the command line, or the Amazon EC2 API, all of which support the copy image action. Both Amazon EBS-Backed AMIs and Instance Store-Backed AMIs can be copied. You can't copy an encrypted AMI between accounts. Instead, if the underlying snapshot and encryption key have been shared with you, you can copy the snapshot to another account while re-encrypting it with a key of your own, and then register this privately owned snapshot as a new AMI. Copying a source AMI results in an identical but distinct target AMI with its own unique identifier. In the case of an Amazon EBS-backed AMI, each of its backing snapshots is, by default, copied to an identical but distinct target snapshot. The exception is when you choose to encrypt the snapshot. The source AMI can be changed or deregistered with no effect on the target AMI. The reverse is also true. AWS does not copy launch permissions, user-defined tags, or Amazon S3 bucket permissions from the source AMI to the new AMI. After the copy operation is complete, you can apply launch permissions, user-defined tags, and Amazon S3 bucket permissions to the new AMI. The AMI creation process is different for instance store-backed AMIs. First, launch an instance from an AMI that's similar to the AMI that you'd like to create. You can connect to your instance and customize it. When the instance is set up the way you want it, you can bundle it. It takes several minutes for the bundling process to complete. After the process completes, you have a bundle, which consists of an image manifest and files that contain a template for the root volume. Next, you upload the bundle to your Amazon S3 bucket and then register your AMI. When you launch an instance using the new AMI, we create the root volume for the instance using the bundle that you uploaded to Amazon S3. The storage space used by the bundle in Amazon S3 incurs charges to your account until you delete it. You can convert an instance store-backed Linux AMI that you own to an Amazon EBS-backed Linux AMI. This involves creating a bundle, but the bundle is then downloaded onto a new Amazon EBS volume. After that, you need to snapshot the volume and create your new AMI from the snapshot. Please note you cannot convert an instance store-backed Windows AMI to an Amazon EBS-backed Windows AMI, and you cannot convert an AMI that you do not own. Using a configuration server can simplify many common administrative tasks. The most common example is provisioning and deprovisioning user access to Amazon EC2 instances. Say that Joe, an engineer, has been given access to multiple Amazon EC2 instances across the fleet, meaning Joe has a private key that enables him to log in with his unique user ID and perform administrative tasks on these instances. But what happens when Joe leaves the company? Without a configuration server, deprovisioning Joe's access to these machines can be a manual nightmare. Using a configuration server, however, a system administrator can easily change Joe's status in the system and roll this change out to all instances in the fleet with a few simple commands. One of the advantages of using a configuration server, such as Chef, Puppet, or Ansible, is that configuration is idempotent. Resources that are created or configured by a configuration server are configured or created only once. If manual modifications are made to the configuration of an instance, the configuration server detects them and rolls them back. This ensures that the integrity of the instance isn't compromised by an accidental change. Most configuration software supports a single machine or standalone model, which means that it is typically capable of managing one to hundreds of servers from a central controller machine, hence the server orchestration term. In a typical environment, you can have a single administrator machine on which you create and edit the configuration templates, store them in the source control system, for example, Git, and use the configuration management tools to orchestrate your infrastructure. We'll now review some typical failures that might occur during the launch of the instances. Automated scripts or CloudFormation templates fail to create instances in different regions. Here, you need to check the AMI IDs. Keep in mind that in different regions, you always have different AMI IDs, so you need to make sure that you set the correct ones in your configuration. Another issue that you might come across is when the instance is marked ready, but the configuration is not complete. Keep in mind that the configuration readiness is separate from instance readiness. You need to take additional measures to check readiness of your configuration. For example, your configuration scripts can send an alert when the instance is fully configured. Another common issue is when the Windows images take a long time to boot from the AMI. The Microsoft System Preparation, or SysPrep tool, simplifies the process of duplicating a customized installation of Windows, but it can extend the time it takes for an image to boot. For instance, readiness. Note that if you are using CloudFormation templates to deploy infrastructure, CloudFormation provides an object called wait condition that can be used by user data scripts to signal to CloudFormation when configuration has completed successfully. The cloud offers you lots of possibilities, but it also brings a lot of questions about how to manage its power and flexibility. How do you update servers that have already been deployed into a production environment? How do you consistently deploy an infrastructure to multiple regions in disparate geographical locations? How do you roll back a deployment that didn't execute according to plan? In other words, how do you reclaim the resources that were already created? How do you test and debug a deployment before rolling it out to production? How do you manage dependencies, not only on systems and technologies, but on entire subsystems? The most commonly used technologies for automated, repeatable deployments include custom scripts and applications in which you can use AWS command line interface commands or AWS API to automate deployments in a variety of languages. AWS CloudFormation is a building block service that enables customers to provision and manage almost any AWS resource via a JSON-based domain-specific language. AWS CloudFormation focuses on providing foundational capabilities for the full breadth of AWS without prescribing a particular model for development and operations. Customers define templates and use them to provision and manage AWS resources, operating systems, and application code. AWS OpsWorks focuses on providing highly productive and reliable DevOps experiences for IT administrators and ops-minded developers. To achieve this, AWS OpsWorks employs a configuration management model based on concepts such as stacks and layers and provides integrated experiences for key activities like deployment, monitoring, autoscaling, and automation. Compared to AWS CloudFormation, AWS OpsWorks supports a narrower range of application-oriented AWS resource types, including Amazon EC2 instances, Amazon EBS volumes, Elastic IPs, and Amazon CloudWatch metrics. The cloud simplifies the migration of systems by making it easier to create parallel environments. There is no need to buy additional hardware to stand up a pilot version of your new environment. You can simply create the resources that you need. However, you still need to figure out how to ramp users off the existing system and onto a new one, a task that is much more challenging than a so-called greenfield or initial deployment. Some common patterns used to bring new systems online in a cloud environment include blue or green deployment. A parallel or green system is deployed by auto-scaling alongside an existing or blue system. The traffic is gradually shifted onto the green system. We'll discuss this model in depth a little later. Red or black deployment. This is a variation on the blue or green method used by Netflix. In this model, the existing or the red system exists in parallel to the new system. Once the new system is fully initialized and running, the infrastructure is considered to be in a red state. Next, the traffic is cut off to the existing system, putting it in a black state. The system is now in red-black mode. The old system is no longer receiving requests, and all new traffic is going to the new system. The black system is kept up and running while existing connections are completed to ensure that the red system is operating without incident. Engineers can bring the black system online if required. Dark launch. Used mainly for testing, a dark launch brings new features into a system without enabling the new feature in the user interface. Dark launches are used to ensure that a new feature works correctly in production and can handle the load associated with a company's existing user base. On this screen, an example of a blue or green deployment is displayed. In this model, a parallel environment with its own load balancer and auto-scaling configurations is brought up side by side with the existing environment. A feature of Amazon Route 53 called weighted routing can be used to begin shifting users over from the existing or blue environment to the new or green environment. Technologies such as CloudWatch and CloudWatch logs can be used to monitor the green environment. If problems are found in the new environment, weighted routing can be deployed to shift users back to the running blue servers. Once the new green environment is fully up and running without issues, the blue environment can gradually be shut down. Due to the potential latency of DNS records, a full shutdown of the blue environment can take anywhere between 1 day and 1 week. As discussed earlier, one of the challenges faced while deploying in cloud is implementing version upgrades. You can solve this problem with the help of auto-scaling. There are multiple approaches. Use the oldest launch configuration termination policy to drain old instances. Old instances will be replaced with the newer ones, launched using the latest version of launch configuration. Bring up 2 separate auto-scaling groups and use Amazon Route 53 and weighted routing to drive different percentages of incoming traffic to the 2 groups. You can start creating new instances and use AWS auto-scaling attach instances to bring new instances into group, and use the AWS auto-scaling detach instances policy to remove existing ones. AWS CloudFormation enables you to create and provision AWS infrastructure deployments predictably and repeatedly. It helps you leverage AWS products such as Amazon Elastic Compute Cloud, Amazon Elastic Block Store, Amazon Simple Notification Service, Elastic Load Balancing, and auto-scaling to build highly reliable, highly scalable, cost-effective applications without worrying about creating and configuring the underlying AWS infrastructure. AWS CloudFormation enables you to use a template file to create and delete a collection of resources together as a single unit or a stack. The 2 major concepts in AWS CloudFormation are templates and stacks. A template is a specification of the AWS resources to be provisioned. A stack is a collection of AWS resources that has been created from a template. You may provision or create a stack numerous times. When a stack is provisioned, the AWS resources specified by its template are created. Any charges incurred from using these services will start occurring as they are created as part of the AWS CloudFormation stack. When a stack is deleted, the resources associated with that stack are also deleted. The order of deletion is determined by AWS CloudFormation. You do not have to direct control over what gets deleted when. First, we'll be creating an Amazon S3 bucket for using the CloudFormation template. You need to decide in which region you want to create the template. For this demonstration, we'll create the template in the Mumbai region. Go to the CloudFormation service under the Management Tools section. Click Create New Stack. On this page, you get various options for designing or selecting a template. We already have a JSON code ready for this template. So let's select the Upload a Template to Amazon S3 option. Click Choose File to upload the file from your system. Select the file from your system to upload it. It's a simple JSON file that creates an Amazon S3 bucket. Click Next. Provide a stack name. Click Next. We'll keep all the values as default and click Next. On this page, you can review the template URL and the stack name. Click Create. Under the Events tab, you can observe the progression of the events related to stack creation. As you can see, the status is being shown as in progress. Click the refresh icon to view the progression of the steps in the stack creation process. Click the refresh icon again to refresh the view. As you can see, now stack has been created. Refresh the page again. Now you can see the status also displays that the stack has been created, which means that the stack is ready to use the resources. Click the Resources tab to view the bucket that has been created. As you can see, Amazon has provided a physical ID for the bucket. Let's now check out the bucket and see it has been created correctly. Let's go back to the console. Click S3 under the Storage and Content Delivery section. As you can see, our bucket is available. Click the bucket name. As you can see, the bucket is empty. Click the Properties button to view the properties of the bucket. As you can see, it has been created in the Mumbai region. Let's now go back to the Management Console and click CloudFormation under the Management Tools section. We'll now go and delete the stack. Once the stack is deleted, this bucket will be automatically deleted. Select the stack, click Actions, and select the Delete Stack option. Click the Yes Delete button to confirm your action. Under the Events tab, you can view all the events related to the deletion process. Click the refresh icon to get the updated view every time. As you can see, the stack and the bucket have been deleted. You have learned how to create an AWS CloudFormation template.
Hey, want to become an expert in cloud computing? Then subscribe to Simplilearn's channel and click here to watch more such videos. To nerd up and get certified in cloud computing, click here.